Hello, good afternoon.
Good afternoon. How's everything?
Hey, very well, thank you. Welcome back.
Morning.
Hope everyone is still having fun with this. Hi, Elliot. It was great to meet Elliot in real life last week down in Lincoln. Okay, this week I wanted to talk about proofs of programs, the application of some of this stuff to programming, and more specifically to what is sometimes called software engineering by the people who hope that such a thing can and does exist, not uncontroversially. So, the first half of this module has been mostly covering the theory of logic and computation. Now I want to start looking at specific applications, and particularly applications here in computer science. This all used to be a so-called theoretical subject, and nowadays it isn't. Now it's become very applicable indeed. And it's been exciting for me to see how this has progressed. When I learned some of these subjects, they were definitely theoretical. They were things you did with a pencil, and people said, wouldn't it be nice if in the future some of this actually existed as software? And now it kind of does, and it's starting to actually get used. So today I'm going to talk about the concept of verification as a form of software engineering, and specifically as an alternative to other claimed reference of software engineering you might have come across, such as the unit testing based approach, which is currently still the dominant one. A unit test can only ever tell you so much. It can tell you if your program's broken, sometimes, but it can never tell you that your program will never break, that it will always work. And those are the kinds of claims that we would like to make using logic, because logic does have the machinery to say for all possible states of the program, they're always going to work. Actually computing the answers to those questions is, of course, the hard part, as in everything we've seen in logic. So that's the basic idea, okay? Verification as an alternative form of software engineering. So then we'll look at a particular style of doing this that is called Floyd-Hoare logic. So we've seen several logics in this module already. We've seen propositional logic, some versions of predicate logic. We had a little chat about modal logic once, I think. Floyd-Hoare logic is another one of these logics. It has its own set of rules which give you a proof theory, and its model theory is the state of software, the state of programs that it's supposed to be there to represent. So we'll have a look at how Floyd-Hoare logic works in theory. In particular, we're going to split it into what's called partial correctness and total correctness. So partial correctness means that if the program halts, it does what it's supposed to do. Total correctness means it does what it's supposed to do and it actually halts. So it actually does the thing it's supposed to do, for sure. We will look at some applications. We'll look at some examples of actual software that is starting to apply this, and actual software that is used for doing it. Hopefully in the workshop we will actually try out some of that software, though it's hosted on a website by Microsoft, which has been a little unreliable over the last few days. It was working yesterday, last time I looked. And yeah, hopefully then we'll see this flow of ideas from something that started as very theoretical and idealistic and has now become a career that you can apply for industrial jobs in next year, if you like. If you remember last year, had this class called Team Software Engineering, and we talked a lot about whether software is or isn't a form of engineering.
Don't remind me.
And both sides of that debate have their advocates and detractors. One of the things I talked about as part of that debate was, what do real engineers actually do, as in civil, mechanical, and electrical engineers. Engineers themselves have something of an identity crisis. I believe there's something like 20 different organizations now all claiming to be forms of engineers, but the traditional forms of real engineering have always been civil, mechanical, and electrical. In particular, these are the forms of engineering which have chartered bodies, so they are really defined as true professions, as in you're not allowed to go around doing civil engineering unless you're a member of that profession, which is very different from computing, right? Anyone can show up and apply for a job doing computing usually, and there's no external body, the British computer engineering profession, who says you can and can't apply for these things. So what is this thing called real engineering? What is it that these people do that gives them their particular professional identity? And it's partly to do with the lack of agility in their design processes. This applies really just to big engineering. You notice I've written electrical engineering there rather than electronics engineering. So sometimes electronics engineering is counted as part of electrical engineering. The electronic systems can be quite small, like computer software systems. Here we're talking about big engineering systems. Who's the person who's going to design a power plant to generate electricity? Who's going to design a bridge? Who's going to design a car? All these things can potentially kill people for real if they go wrong. And what is distinctive about this design process is that doing a build and doing a test is very, very expensive. And so you can't do what we call agile methodologies in these fields. Computer scientists have a relatively easy life compared with these people, because we can just try something out, type make, and then type go, and we find out whether or not it works. And the cost of doing that is basically zero in most cases. And because of that, we've constructed this particular way of working, which we call hacking or agile, depending on your point of view, where we go round and round very fast, trying stuff out and breaking things. Facebook, I think, once described its motto as move fast and break things. That's the agile approach. You can't do that if you're designing a nuclear power plant, because building the plant, as distinct from designing it, building it is going to be very, very expensive. And when you press the button to begin the build, you're going to sign a contract with probably with a whole bunch of companies who are going to come with trucks full of concrete and steel and follow your design, and you can't go back on your design. The design must work once you've taken the decision to do the build. Having done the build, you might attempt to test it in a few ways. Say you've just built a bridge, you might drive a few vehicles over it or something, just to make really, really sure, but you're really expecting it to pass the tests by that point. You're going to be in a lot of trouble if it doesn't pass the test. And then, of course, if any of these things go wrong that you've built, people may die, or from a business point of view, you are going to get sued, basically, and that is also going to be very expensive. So, professional engineering has evolved a particular way of dealing with those kinds of challenges, and you can't take the agile approach in those situations. You must have this more formalized, what we derogatorily refer to as the waterfall model here in software. You have to do your design first, and then you do the build, and then it really has to work. but there's actually an extra step in between making the design and building it. There's this process of proving that your design is going to work, usually by using mathematics. For example, let's say that you agree to build a bridge, okay? Professional engineering is pretty much defined as solving problems in response to a client's need. So, the client is going to specify what their need is as a set of conditions. So, this bridge must be able to support up to 100 cars on it at the same time. The cars will be going no more than 60 miles an hour, say. The wind speed is going to be within a certain range. The other weather conditions will be in a certain range. The temperature will be in a certain range. And at that point, we're going to sit down and sign a contract which says that's what I'm going to deliver. And if I deliver it, you have to pay me. And if I don't deliver it, maybe you can sue me. Whatever. That's the contract. So we start the whole thing by writing that specification and both signing up to a contract that it's going to be delivered. So at this point, I'm going to start the design process. I'm going to start sketching, and this is what I think of as the beanbag phase. I'm going to kick some ideas around. This is a creative process. I might just sketch something on a piece of paper, or I might sketch it in a CAD program. At this point, I'm working more like an artist. I'm creating ideas from intuition. I hope these things are going to work, but I don't know yet because I've not done thinking about whether they're going to work. They're just my best guesses what might work. Now, if you're a computer person, at this point you press the button and say do a build and find out whether or not you were right. Your design is a hypothesis about whether or not something is going to work. But if you're one of these engineers, you can't do that because it's too expensive. And so you have this extra step where you're going to use your analytical skills, usually mathematics, maybe some kind of simulation or cut down model. Usually it's a mathematical physical theory, such as the theory of forces and stresses and strains that appear in the bridge. And you're going to take off your creative artistic hat at this point and put on your analytical hat. This is a form of rhetoric. This is a form of logic. Rhetoric creating the thing. Logic is analyzing it. And you're going to make assumptions as realistic as you can. You're going to use all that mathematical apparatus to try and pick holes in the thing. You're going to find any failure cases, flag them up, get them fixed. Maybe you iterate a bunch of times. You're going to have to update the design, go around and do the analysis again. But once your design has passed this mathematical verification phase, only then are you going to do the build. Now you're going to call up Balfour BT or someone and get them to start delivering concrete to the bridge site. And at that point, it really has to work, right? If it doesn't work afterwards, you're going to get sued. Or rather, you're going to get sued if it doesn't work under the specified conditions. So that contract we made at the beginning is very clear about what is whose problem, right? It's your client's problem to provide the specified conditions. Your problem to make the thing works within those conditions. So I think a lot of engineers would love to be more agile. If it costs zero to actually do a build of the bridge, it would make their life a lot easier if they could omit this analysis phase altogether and work in just the same way that we do. The process would go much faster because this is hard and it's slow. And in fact, there seems to be a bit of a movement within engineering at the moment to try to be at least a little bit more like us. I believe NASA has started looking into small parts of agile physical methodologies. Now we have things like 3D printers that makes the build system faster and cheaper. So there are some parts of traditional engineering that are wanting to become more like us, but there's something big like a bridge you pretty much always have to take this more formalized approach. So, here in software world, we are normally very lucky compared to those people. Normally we can just type go, do a build, do a test, and then we iterate around to make our design a little better every time. Until we run out of time or money or motivation, and then we stop, and then we have a program that works most of the time, and we're usually happy with that. And this is probably what you're doing in your student projects around this time of year, right? You probably all have something that is kind of working now. It's passing your unit tests. It makes a couple of users happy, but you're still finding little bugs in it every couple of weeks, right? Little things to fix, little things to polish, and you can never really get rid of all the bugs. You can just have some probability of finding another one and fixing it until you run out of time. And this is the limitation of testing-based development. When you write a suite of tests, they can only ever prove that there exists some state of the system. So here we are quantifying over system states, right? That means roughly the values of the variable and the state of the stack, and possibly the state of the program counter. All the numbers you need to specify the state of execution of your program. So a failing test will show that there exists some state of the machine where your program fails, where it doesn't work. And they're not guaranteed to find that state, but if they do find it, then there's definitely at least one failure case that you can then go and fix. But a test suite can never prove that your system will not ever fail, okay? This says there is no state X such that the system will fail in state X. Actually, in theory, your computer is always a finite machine rather than a perfect, unlimited memory machine. Now, in theory, you could actually do this because you could always just search through every possible memory state of the machine. But in practice, that's going to take you longer than the age of the universe, so it's still not going to happen. So a test is also a form of dynamic analysis rather than static analysis. Static analysis is when you look at the code as an object and inspect it, whereas dynamic analysis is when you actually run the code. You actually perform some execution. Maybe a smaller execution than actually running the whole system, but some form of execution is going on. So you still have to build your system. You still have to do some sort of execution to get through your tests. And this works pretty well for probably 95% of software. You can keep testing and adding more tests and getting more complaints from users every time they find something that breaks and keep on fixing them. But software as a whole has a reputation for being, how do we put this politely, for not always working, right? If a customer goes out and buys a car, a new car at least, they really expect it to work, or at least to be safe. They're going to get very cross, and your reputation is going to be very bad if the thing doesn't work. If a customer goes out and buys a new piece of software, they pretty much expect it to be crashing and chucking out error messages, because that's what people think software does. Almost all the software you buy is going to crash somehow at some point. So that is happening because of the design process. It's because you can never eliminate every single failure with this test-driven methodology. There can always be some case that you've just never seen as part of your test. So economically, customers generally seem quite happy with that. They would rather pay a bit less for a piece of software that hasn't had as much analysis go into it. But when they buy a car, Probably they legally have to pay for a car that's gone through that analysis process. There are laws passed by the government that say you're only allowed to sell a car if it's certified according to certain standards. Now, in some cases, you may have to build software to the same kinds of standards as those hardware products, and particularly this comes up when the software is going to exist as part of a combined software and hardware system. For example, in robotics, you have programmers and mechanical and electrical engineers all working together, and usually having some quite strong disagreements about all of this, because the way that the engineers have been brought up to think about this is very different from how the software people have come in. If you join a team full of ex car designers and you come in saying, oh, we'll just hack it together and see if it works and then we'll fix it, they're not going to go with that. They're going to want to see that 6 months process of doing it properly in the first place and making it safe. So, the major cases of this are things like, aircraft autopilot, nuclear reactor control software, self-driving car control software now. You can see these things are coming closer to being consumer products. This used to be a pretty niche area, right? Not that many people were writing or manufacturing nuclear reactors, but if you believe the car companies, there's going to be a lot of people manufacturing and buying self-driving cars pretty soon. So in these cases, you are going to have to think more like a traditional engineer in terms of absolutely being safe. You need to prove that the thing is going to work. It's not enough just to test it in a bunch of cases and hope that it works in the remaining cases. You're going to need to prove that it will work in every one of those cases. And these are systems very expensive to build, very expensive to test. People are going to die if your software does not work. More recently, similar ideas are flowing into pure software systems that don't have any hardware attached. We have this new GDPR regulation, which is now making it similarly expensive to get sued for a data breach as you'd get sued for killing someone in a car accident with your software. The penalties for data breaches are now so severe that building the software properly could actually now be cheaper than getting sued for a data breach. The causes of data breaches are likely to exist at any level of your software. Okay, if there's ways that your whole system can crash, if your kernel can crash, if you're using a compiler that doesn't do what it says on the tin and your compiler is generating buggy code, all of these things can be exploited. Usually these are not accidents. Usually these are caused by malicious exploits. Someone's actually worked hard to find these cracks in your system, and they're going to deliberately put you into these states that you haven't tested, and they're going to break them. So traditional applications of doing it properly have always been in these kind of hardware mechatronics linked systems, but we're seeing it move into pure software now. There's an operating system running on the new Mars rover, and that operating system has to really, really work, because if it crashes, you can't just send someone out there to turn it off and on again. Maybe we should just design all software to actually work. What would happen if we worked like the real engineers and built stuff that actually worked all the time instead of this agile testing based methodology?
We would lose a major source of entertainment in the form of bad video game physics videos.
So, yeah, it would be very different, wouldn't it? We'd probably all have to wear a suit to work every day for a start, and maybe this would link more into the idea of this being an actual profession with standards and stuff. If you hire a chartered programmer, maybe they'd actually promise to deliver stuff that actually works. From a customer's point of view, that's going to make it all much more expensive, right? Because we like hacking. That means you can pay us less to do it because it's actually fun. So, there's economics in this. At least until recently, customers have seemed to prefer to buy stuff that is cheaper and doesn't work quite as well, except in these fairly niche engineering-based cases. One from Matthew.
Someone, I was listening to the Type Theory podcast the other day, and they all very casually bring up how verification and proof is obviously a lot harder than testing. I was wondering, actually, since you brought it up here, how would you actually distinctly compare them on like a complexity basis? So the cost, like actually algorithmically, of choosing, obviously a unit test can't enumerate all of the possible states, but to some degree of accuracy, say 5%, if we're going to be like the rest of academia, how would you actually compare the complexity of going through a formalized unit testing versus doing a complete proof of the program?
Yeah. I don't think I can give you a straight answer on that. I can hand wave for a couple of minutes. It's probably traditional. And it's often the case, as we'll see, that the proofs end up being considerably more complex than the underlying program, for a start. So, when you write tests, it's annoying, isn't it? Sometimes has anyone ever written a system where the tests are bigger than the program? Anyone ever tested that much? It can happen sometimes, but a proof can be massively longer than the original program. So we're using the same machinery here as the mathematicians use to verify their proofs. We talked about Fermat's last theorem last time, I think, and Fermat's last theorem is about 12 characters long, right? And the proof for it is 2,000 pages of human readable maths. To try and turn that into a formalized proof is possibly going to be millions of pages long, all to verify 12 characters of equation. So yeah, these things can get very, very big. We would like to automate as much of the work as possible rather than do it manually. We could talk about that. But yeah, tests can also get pretty big as well. I have no idea how you would formally compare the complexity of one with the other. Maybe a nice PhD topic for someone like that. Okay.
Thank you.
Yeah, this is not an easy process, and that's the reason why no one is doing this for your Android Space Invaders game. Whatever. It's not worth doing it for an Android Space Invaders game, but it is worth doing it for a nuclear power station, or possibly for a self-driving car with current technology. Okay, so here's how this could work then. As in real engineering, we're going to start by agreeing a contract. And the user of the system, the user might be ourselves, our future self, whatever. Often you write a bunch of functions that all call each other, and you have to put on different hats when you're the owner of one function. Then you go and act as the user of the same function later on. But at every level of the design, there has to be this contract saying, here's what I actually need you to do. And the other half of the contract is saying, I will do it. I will return the value within this range and having these properties, as long as you give me inputs within these ranges and having these properties. And if you try and call my function with something that wasn't in the contract, then it's your problem. If you call me with something that is in the contract and it doesn't work, then it's my problem, and we know who to blame and who can actually fix it. Yeah, so we would first agree a contract. Yeah, we would then put on our artistic hat and sit on our beanbag and come up with a design, which is our best guess at something that might hopefully work. Another one from Matthew.
Don't you need to be more specific than like input to the function? Because obviously, as you said on the last slide, our program obviously depends on X, where X isn't really even the state of the stack, it's the state of the entire system and how the program was built, because our program's different depending. If you actually look at the program P, we've written a program P, but that obviously depends, like when it actually gets run, on whatever compiler's used and whatever architecture we're on.
Yeah, right. So these contracts could get pretty complicated, right? If you're really basing your contract literally on the state of the machine that is acceptable and unacceptable, that's going to be a pretty detailed contract. Wouldn't it be nice if we had programming languages that didn't have any state, and then these contracts could be really simple, and they could only talk about the inputs to the functions. Yeah.
Oh, wouldn't it be nice?
That would be
No, there's nothing. I can't think of any kind of languages that are like that. All of the programs I've ever written are imperative and very stateful. So.
Yeah, but they actually do useful stuff as well. That's the hard part with the nicer languages. I'm still trying to figure out how to draw a triangle on the screen using standard ML. It's been 20 years and I still can't find a way to do it. Because it's like the screen is state. Right. So we've done this artful design process now. Yeah, we've, like the engineers, we've sat on a beanbag. We've sketched out something that is our best guess about something that might hopefully work. That is a creative process. And at that point, before we go off and do the build, we are going to take off our creative hat and put on our suit tie, and we're going to go into analysis mode. We're going to take that design as an object and we're going to throw all of our mathematics at it, like the engineer does for their bridge, to try and prove as much as we can about its properties. And when we're confident that the thing's going to work, then we'll type in make and do the build, and then it should just work. There isn't even a testing step if you've already proved that it's going to work. So for example, again, what could this look like then? You might agree you're going to make a function. It's going to have certain conditions on the inputs and the outputs. You might sketch the program in your favorite text editor. At this point, the program is a hypothesis. It is not a finished thing. You're now asking a scientific question. Here's something that may or may not work. Does it work? And then we are going to use the theory of logic and computation to try and prove that it will actually work, right? Like the bridge. Try and prove that it isn't going to fall over under the specified conditions from the contract. Yeah. Then run make, and yeah, probably like the bridge builder, you are going to get sued if these kind of things don't work, because a lot of money has gone into the process by now. This is especially the case for hardware, by the way. Intel got one of these wrong in the Pentium floating point unit, which I think was many billions of dollars. Recalling all the Intel processors in the world and remaking them is not a cheap process. One from Gary.
Yeah, so I think that's interesting. One of the things that I think when I think of electrical and mechanical and civil engineering is that there's no sort of concept with open source and closed source in that sense, but on a software perspective there is. So there is someone to sue. How would you sort of think about that? A sort of a leaderless crew of bandits writing some awesome software that's
I mean, this is actually a really nice question, and it's a really nice it's a really nice way of answering how open source programmers could actually make money. So, we all like our open source. Again, this is a big difference with the hardware engineers. Computer scientists in general prefer everything to be open, but at the same time they need to eat, which the hardware engineers laugh at us for being confused with that. So in what you get in physical engineering is this notion of a legal product. When you've designed a car in a certain way and the design is finished, that concept of being finished is much more formalized than it is for our software. Right? When you update your operating system because you just found another load of bugs in it this week, you are used to just pushing that out, and all your people are just going to update it, and the product is constantly changing. It's not like that in physical engineering, because when you finish your car design, there is then this extra certification and legal process, and the outcome of that is a legal document that defines exactly what the product is, and it says that it is passed a certain set of tests, usually to meet some international standard, an ISO standard or BS standard, and that certification process takes a lot of time and money, and it's going to be very hard for you to update the design by saying, actually the wheel should be in a slightly different place now, because you're going to have to do that whole process again to get certified. So with software, there is an opportunity here, it seems. There is always going to be multiple versions of open source systems floating around. The whole point is everyone is constantly forking it and doing their own thing. And you probably can't verify all those different versions very easily, unless we ever figure out how to completely automate it, which we can't currently do. So, there is an opportunity then for some versions of your open system to be jumped on by these verification experts. They're going to do the work of actually proving them and certifying them. And maybe they then have some legal mechanism where they can charge money one way or another for having done that work. So for example, there are the versions of Linux like Red Hat, which have become certified in various ways. So we have Fedora Linux, which is the real community version, and we have Red Hat, which is backed by a company and which is providing some kind of guarantee that the thing's actually going to work. And Red Hat are there. They're primarily there so that they can be sued if the system doesn't work. And many customers are very happy to buy basically the same piece of software off them as the open source community version. And they're just paying for that assurance. They're paying for the ability to sue someone if it doesn't work and to move the risk around. So maybe we'll see something like that. Open source hardware has recently become a thing. We're running a few open source hardware projects here at the moment. It's a much newer thing than open source software. There aren't the same kinds of definitions as you get in the GPL and the BSD licenses. It feels a bit like, I don't know, the early 1990s, where in software people were arguing about what should open software actually be, how should we define it. There are people writing papers about what is open source hardware. And yes, some of those concepts get kicked around. The idea that a product isn't a very free software friendly word, right? It sounds like something that is going to be sold for money. That doesn't have to be. A product could just be something that is defined as a thing, a legally existing thing. So there are ideas that float around where an open hardware project could be certified as being open hardware, at least. and then when it exists with that status, that enables it to get combined into other people's open hardware systems and so on. And you know, that's happening both with big hardware systems like robots and also with small digital logic systems in chip design. You know, when you go to the RISC-V processors, some of them are being developed as entirely open hardware, and they have exactly these questions. You know, how are we going to certify this when everyone can go around forking it? Yeah, probably what's going to happen is that certain people are going to create trademarks, and they're going to stamp the trademarks on various open systems and then charge more money for them because they've definitely been verified, and the trademark is their reputation getting stamped on there.
Yeah, just looking and within blockchain technology, actually, with Ethereum, there's a business called Open Zeppelin, which will sort of you use their functions to complete your sort of smart contracting, because you could write your own and lose a lot of money, or you could use that. They're all open source and make sure it's sort of working, and they will guarantee it works with compiler updates and all this sort of stuff. So yeah, so I sort of see it's beginning a little bit from decentralized systems. And that's
yeah, it seems that there's a lot of money is made in this world not through actually doing anything, but by backing things, just by putting your reputation onto stuff and saying that it's good. You know, that's what a record company does. It's what a book publisher does. You know, actually making stuff is the easy bit. Promising that it's really going to be good is the harder part, and where a lot of the money seems to end up. So I just wanted to show you the state of the industrial market for this. As I said, when I started studying this, it was a very theoretical, you know, a research field. And can you guys see my screen? Yeah.
Yeah.
So you know, this is just
yeah, I can see it fine.
Yeah. So you know, let's see who's hiring in the UK. This isn't even Silicon Valley, right? This is UK. Who's hiring for verification? You know, so look, here's Apple, here's ARM, of course. ARM has always been a big advocate of this. Look, there's a little bit of academic stuff. You know, that's in the minority now. There's a postdoc at the University of Manchester. Siemens, we know. Airbus, right? Low risk. I think we mentioned low risk in architecture. You know, these are doing fully open hardware. This is RISC-V open all the way down to the transistor level. They're still paying people to do it though. Yeah, somehow they've got funding to make a business case for all of it. So you know, almost entirely companies like here's Amazon, right? Amazon's doing some kind of automated reasoning verification in there. What else is here? Here, defense, self-driving cars. 5AI is a self-driving car company. They want to make sure that they don't hit anyone. You know, nuclear safety, and so on. So this has become a pretty real area, right? Yeah. Rolls-Royce control engineer. And then we're down to another academic one. You also notice most of these jobs don't have salary information on them. That usually means they're going to pay quite nicely. It means they're going to be open to negotiation. I think this is the only one that has a number on it, as far as I can tell. It's 65 to 75, and yeah, probably that is going to be open for negotiation as well. One from Gary.
Yeah, it was just you mentioned the self-driving, and just a thought popped into my head is that they'll verify that they don't hit you, but on the other side they can also absolutely verify that they will. In a sense, that's a funny sort of concept, I suppose.
Yeah, so I'm part of a European project that is looking at some of this. So I don't know if you've seen the work I do with my PhD student Fanta. She studies hitting people with self-driving cars. But it's for the purpose of not hitting them, but we study hitting them to do that. But there's some other people on that project who use the same kind of tools we're going to talk about here to try and make these formal proofs. You can consider the system state of the car. How fast is it going? What control signals is it giving? What's the environment? And you can try and actually prove that you'll never get into a situation where you're going to collide with someone else. It gets even more fun when there's multiple agents, right? What happens when two self-driving cars are heading towards each other and one of them has to get out of the way? Yeah, that's going to be a lot of fun. Okay, that's the motivation. Let's take a look at how we might go about doing this. So there are many approaches to verification. We're going to look at what is called Floyd-Hoare logic, which is the classic approach. Kind of originally suggested by Floyd before Hoare, and then Hoare created the modern version that we see here. I think Floyd did it in the days before written programs were even a thing, and everything was just done with flowcharts that were basically finite state machines. And then Hoare turned it into a notation for programs in the way that we think of them today. So the basic idea then is we are going to use logic, and we're going to make some statements about what is true at various points during the program's execution. And remember, logic and truth are two different things, right? This is all about proof theory. Truth is all about model theory. So when we talk about truth, we're saying the actual state of a program is having some property. When we talk about proof, we're simply doing symbol manipulation and deriving strings of symbols from other strings of symbols. It's when you go to truth that you make that connection to the real world, as in the state of your actual physical computing machine. So at the very least then, we're going to make two sets of these statements. We're going to make some statements about what is true before your program runs, and these are called preconditions, here written as phi. And we're going to make some statements about what is true after your program has run, called the postconditions, or psi. And in general, we're going to notate them like this. So precondition, a bunch of stuff is true. You run your program, P, something else is true at the end. And this whole thing is a fact. It's a logical fact that we are going to try to prove or disprove. Okay, so think of this as, as with the MIU system and the lambda calculus and everything. This whole thing is a string, okay, including these funny looking brackets. Why does Hoare insist we use these funny looking brackets? Any guesses? Right, it's because most programming languages already have other uses for the brackets. Okay, when we've seen these other logics, they've been quite small and they've only had very small grammars and sets of symbols. Whereas, yeah, probably any real-world programming language today already has the symbols for normal brackets and curly brackets and square brackets and probably triangular brackets. And so he's just run out of brackets. So we want to make it clear that we can put any program, any text string for the program there. And so therefore we need a actually brand new symbol to show that we're doing something else. So these, possibly these are called Hoare brackets nowadays. I don't know if there's a typographical name for them as well. Let's call them Hoare brackets here. Yeah, the Hoare bracket then is used to show that this isn't part of the program. This is saying something about the state. This is not, however, meta logic, because this whole thing is just a string within the system. Okay, so sometimes you see logical texts that use things like double square brackets when they want to talk about meta logic. So we're not doing that. There's no meta logic here. This is a purely logical formula. The whole thing is one formula and we're just using those brackets so that we can say things about programs that use all the other kinds of brackets. Okay, that was quite abstract. Let's look at a very simple example. So here's a precondition. Let's assume that at the beginning of our program, x equals 1. Now, at this point, it's useful to use very correct notation. Okay, so this symbol, colon equals, that you find here, this is called assignment. Okay, this isn't making a claim about what the world is like. This is saying go and do something. This is an imperative instruction to make x become equal to what was previously x plus 1. Okay, so this is a statement from an imperative language. So it's a command to actually make a change to the world. Whereas this symbol, this is a logical symbol. This is saying the value of x is the same as the value of the symbol 1. So inside a programming language, that is often written as a double equal symbol, just to force you to make it different from the assignment operator. So, okay, here's our precondition then, and you think of this as a contract. You are going to write this program in response to your customer's need, and your customer has said, I promise that x will always be 1 at the beginning, and your customer also says your job is to ensure that x is 2 at the end. Okay, so this forms your contract, the precondition and the postcondition. So given those conditions, that contract, you then go away and you creatively invent a solution. You make your best guess as to what might work to solve the problem. And if this is a trivial example, so you're going to come up with this idea, let's make a program which takes the current value of x, adds 1 to it, and assigns the value of that to the new x. So there's actually quite a lot going on there when you really think about it. So now you have what is called a Hoare triple. A Hoare triple is the precondition, the program, the postcondition, all written together. And again, we're going to think of this whole thing as a string, or as one formula in our logical system. And this is something we would like to know, is this a theorem or not? Because if this is a theorem, then we've proved that our program really, really works. Why have we not proved that it absolutely 100% guaranteed works? Why have we only proved that it really, really works?
Sorry, could you repeat the question?
Okay, let's say I run this through all my best logic and proof, yeah, whether that's a manual mathematician or an automated system. Why can I never be absolutely 100% guaranteed certain that my program does what it says on the tin? Why can I only be really, really sure, but not 100% certain? Okay, so how do I do this logic and proof process? What am I going to do?
We're assuming that the logic itself is sounding correct. Yeah, okay.
Yeah, we're assuming both that our logic itself works and also that any software implementation of it we're using is working. Or if we're doing it manually, we're assuming that our manual application of logic is working. Yeah, again, wouldn't it be nice if we could prove that the logic actually worked? Right, that was Hilbert's dream in the first place, and we can't. You can take one verification system and prove that it works using another verification system, and people do this. You can go and prove that one works using another verification system, but you can never have a system that proves its own accuracy. You're always relying on someone else. So it's actually very good for the world to have many different software implementations of verification, because it at least gives you a bit more confidence if a bunch of them can verify each other. Or the more of them you see verifying the same proofs, the more belief you have that they're all actually working. So this is related to this idea of contract-oriented programming that we've talked about in software engineering, but as more of a dynamic analysis technique. So you've probably all written little contract-oriented programs like this. If you write your function with regular assert commands, so most languages will give you an assert command, or it's trivial to make your own. Assert is just a function which checks whether something is true, and if it isn't, it throws an exception. So if your program has got to here, you now know that the assertion must have been true, because you wouldn't have got here if it wasn't. So you can do contract-oriented programming without formal verification, just using these assert statements. This could be your function. You might call this define f of x or something like that. And this gives you a dynamic approach to making a contract. You're just saying, I'm going to throw an exception here if my user broke their end of the contract, and I'm going to throw an exception here if I broke my end of it. So we're not actually going to know that the program always works, but we will at least know when it falls over, we'll at least know whose fault it was and who needs to go away and fix things. So yeah, think of the precondition as an input requirement or an assertion, and think of the postcondition as a promise or an assertion sitting at the end. So these assert commands are going to show up in verification systems, but they're different assert commands from the ones you've seen in dynamic analysis. In dynamic analysis, this is implemented as throwing an error at runtime if it doesn't work. In verification, and you'll probably see them written with an underscore in verification, they are not executed at runtime, but they exist more like comments in your original code. They're there for the verifier to use and to figure out whether or not they hold up as a form of static analysis. Okay, let's go to, what's the difference here? Okay, can anyone spot the difference? What's new in this program? This is a slightly more sophisticated version.
We have types.
Yeah, we have types. What else do we have? I'll show you the first. The first one promised that x was a particular value, all right? You see now we're just promising that x is in a range. We're saying x must be an int and it must be greater than 0. Okay, good. And so we've got a similar promise on the output. We're going to say, as long as you give me an int greater than 0, I'll give you back another int greater than 0. And if you don't have types built into your language syntax, you can do this manually through contract-oriented programming again. So, for example, this combination of being an int and being greater than 0 means that x is an unsigned int, right? Means it's never going to go negative. So you could implement this by writing something like this: assert that x is an unsigned int and that it's still an unsigned int at the end.
Then we actually also, so technically they could be greater or equal to, but that's pedantry. Then we also have to technically make some guarantee of it not being between two integers.
So you can write whatever you want in a for a uint, you mean?
Yeah, so in order for it to be an integer, it obviously can't be a decimal, right?
Yeah, okay, so being a uint is actually a stronger condition, isn't it? Because a uint has a maximum value as well. It has a large finite maximum value. Yeah?
Yeah.
Okay.
And since we're also in the abstract. Oh no, because it's obviously a precondition that it's an integer. Yeah, that's interesting.
Okay, good. So yeah, types are a funny one because many languages choose to treat them differently from all these other kinds of assertions. It's unusual to have a language where you can specify that x must be greater than 0 directly in the language, whereas it's very common to have languages where you specify x must have type int. There's often a special syntax for that. But when you think about it, it's exactly the same idea. And when you go to languages like Haskell, Haskell gives you these very powerful type systems where you can put in information like this as part of the type. So for example, in Haskell, you can say this function is only going to run on even integers with the type of even ints, which is harder to do in languages that are typed but not as sophisticatedly typed. Okay, let's take a slightly larger example then, again in a C-like imperative language. And in this case, I've written it more as a conventional program notation. Yeah? The program is split over a number of lines. The precondition is written before those lines and the postcondition is written after. But if you remove all the white space from this, it's the same idea. You could have just put it all on one big line like that. I've just put in some white space characters to make it look prettier. This whole thing is still one string, which we are hoping to prove is a theorem later on. So remember this symbol, this is called top, meaning true in the model theory. So this is something that is just always true. This means we're not assuming any particular preconditions. This thing is always true, no matter what. So then we have the program. You can see we start off by x is the input effectively. A is going to get assigned. We're doing tests. We've got a variable y. We've got y being assigned in two different ways depending on the value of a. And then we're going to assert at the end that y is always equal to a plus 1. Okay? And maybe just take 2 minutes and see if you can convince yourself that this program actually does that. Okay? I'll give
Did we remember to do attendance codes?
Yes, they were in the text chat. Again.
I must have missed those. Oops. I must have arrived like a couple of minutes after you'd posted them or something.
So, anyone want to offer an argument about why this works, or why it doesn't work? Even?
I think the logic itself, like within the program, is sound. However, do we really not depend on any priors? Because where does x come from?
So yeah, we haven't placed any conditions on x at all. X could be anything.
Yeah, and then so the post condition then is that y is a plus 1, but a is something that we assign within the program itself.
Yeah.
Which is weird. I think the logic itself makes sense, or rather the program makes sense, but not. Maybe it's just a syntactic thing.
There could well be a bug either in the program or in the contract. Yeah, you could equally well find a bug in the contract. In fact, yeah, you can actually prove that this is not fulfilled, can't you? Look, in this case, y is becoming equal to a, and here you're asserting that it's equal to a plus 1. Yeah.
Yeah,
So
I noticed that one as well.
yeah.
Like,
how about if we turn this into an x?
if we turn it into an x, then it would be correct because a is x plus 1. So if y equals a, then y would equal x plus 1. I did also realize that even in this first case, I'll just put it in red. Even I don't know if it's already been mentioned. It very easily could have been, but in this case as well, we have the same issue. Because if a minus 1 is equal to 0, then a equals 1. So if then y equals 1, then you effectively this statement and this statement are doing the exact same thing. Because if a minus 1 equals 0, then a equals 1. So then y equals 1 is the same as saying y equals a. So all this code is doing is saying y equals a, and therefore if y equals a, y can't equal a plus 1. However, if a equals x plus 1, so then changing it to y equals x plus 1 if y equals a is correct.
Okay, so you convinced that works then? Are you convinced?
I'm convinced that this, with that modification, does work, but its original form it didn't.
Yeah. Okay, so what else could we deduce from that then? Is this the optimal program for doing this calculation, or could we replace it with a shorter program?
We could replace it with a shorter program by just taking out the if-else statement and just putting it as y equals a.
So if we just get rid of all of that, yeah.
Yeah.
Could we simplify it even more?
Yep. If we got rid of this and changed this to y.
Right, and then the assignment would say exactly what the post condition says. Yeah.
Yeah.
Then it would definitely work. Yeah. So you can see there's going to be some connection here between code optimization and verification, right? If you can prove the conditions hold up, you can then go around looking for other programs that have the same effect, but may have nicer properties, like being shorter or taking less time to run. Good. So this also illustrates, completely intended, of course, this also illustrates the danger of making bugs in your specification itself. Yeah? These can get just as buggy as the underlying code. And indeed, that's been a major reason for the lack of uptake of formal methods in general until very recently. Okay, good. Now, in the program we just saw, there was a single precondition and a single postcondition, right? And this whole program sat in the middle, and you had to do some fairly serious thinking to convince yourself that we could get from there to there with the program. Yeah, and this is a tiny little program, and you still had to think quite a lot to go through. So we can make your life easier as a verifier if we give you some hints as well. Okay, as well as giving you a precondition and a postcondition, we're going to put in a whole bunch of intermediate conditions. Okay, so you might have seen actual recipes that are written like this. They really annoy me when they don't put the assertions in or brackets now, because when you follow a recipe, you want it to be very clear what are the things you have to actually do. Okay, and some recipes will mix up these instructions for what to actually do with other stuff like assertions, claiming that the system is in a certain state. So for example, here is a contract-based recipe for making a meal, and the precondition is that you have some chicken and you have some rice. Okay. It would be really annoying in a recipe if you got halfway through and then it asked you to find some rice and you didn't know in advance that rice was going to be needed. So it's common at least to give you a list of ingredients as your preconditions. The post condition in the contract is that you are going to get a meal which is safe and ready to eat at the end of it. Yeah. So whoever wrote this recipe says, I'm going to promise to deliver you this as long as you satisfy this at the beginning. Follow the instructions, everything will be okay. So now, rather than just having the pre and post conditions, we're going to check that things are okay as we go along. So this is an instruction: you chop the chicken, and the state has now changed. We're going to make a new assertion. You now have some chopped chicken and you have some rice. Okay, so the chicken we had has now turned into chopped chicken. Now you fry the chicken. So here's a new assertion. The state of the system now is that you have some chopped fried chicken and you have some rice. Now go and boil rice. Now you have some chopped fried chicken and you have some boiled rice. Put the chopped chicken and boiled rice on a plate and you're done. Your meal is safe and ready to eat. What could go wrong with this? This isn't a formal program. It's written in English. It makes a whole bunch of assumptions. What could you potentially sue the recipe writer for here if you didn't actually get your meal out at the other end? What could have actually gone wrong?
Salmonella.
Okay, so maybe we should have checked the chicken at the beginning. Yeah, maybe we're only going to make a contract that says the chicken is safe at the start. Yeah?
It doesn't tell you to chop the chicken safely, so you could sue them because you've got no fingers.
Yeah, chop the chicken safely, right? What are you going to chop the chicken with?
Oh.
Yeah.
It doesn't tell you to get a knife or a chopping board, or to preheat the oven, or to even have an oven.
Time frames either.
Yeah, right. Nothing to do with time. Nothing to do with equipment. This is where
the only equipment it tells you to get is the plate.
But that's even the plate.
No, that's also.
Yeah.
Oh, we don't even tell you to get.
Yeah, what is this plate of which you speak? I hate it when this happens in a real recipe. You've spent.
I've now just got this horrifying image of someone like they've got this rotten chicken and a bunch of stale rice, and they're trying to chop the chicken with their hand, boiling the rice just on the they don't have any water or any saucepan. They just put the rice on the hob. Oh, God. I
actually did one of these the other day, and I was on like step number 7, and it says put the rice on to simmer for the next 45 minutes. So I did that. Went off and studied my logic and computation book for 45 minutes. Came back and looked at step 8, and then step 8 says, while the rice is simmering, go and chop the chicken and do all this other stuff so that it is ready to put in the final mix. And you can't put that in step 8. It needs to have been given before you did step 7, or it isn't going to work. There's a theory that you should read the recipe before you implement it, which I totally disagree with, because a recipe is a program and it should be written in a way that has all the information needed at each step of the execution.
While rice is in step 7, while rice is cooking, execute step 8.
Well, this is actually interesting because of how it links into what we were talking about before. Even in an engineering context, like real engineering, who we have a lot of respect for, really, we said that the verification would inform the design step, but the design step will actually also, in some form or another, be informing the contract, because the contract that we're creating with the person is probably going to be based initially on some informal specification of what they're trying to achieve, and then that gives us a wide problem space that we need to optimize in. And probably you're going to, you know, the fancy now is working with the client in order to get what they actually want, not what they're asking for.
Yeah, right. Because no one could have written this contract properly in advance, could they? You know, it's only now we've figured out that we've got to put a plate and a knife and a cooker in here as well. So, you know, yeah, now we're going to have to go back to the client and say, are you happy to add these things to the contract? Yeah. No, you have each of these things available. Yeah, and the safety of the chicken and all this other stuff is coming up. And, you know, if you attempted to verify each of these claims formally, if you have a software tool that is doing this, you know, it will flag this stuff up. It will say your verification has failed because you need to have a plate. Yeah, so that tool will now tell you that something else needs to go in the precondition. Good. Yeah, you know, the other thing, recipes are interesting because you can do things in parallel, right? We talked about parallel programming a long time ago. You know, this frying of the chicken, maybe the frying and the chopping could be done in parallel with boiling the rice, because this takes the longest. You know, anyone fancy verifying a concurrent version of this program? That's actually a really good use of verification, because doing anything with concurrency is hard, and you really need all the help you can get with it. Yeah, if you have any sort of automated tool to help you find problems in a parallel program, then make the most of them whenever you can.
Something else that I thought was interesting about this is, in part, so we talked about separation of verification from hacking on a project, but in part, if you're writing a project and you're following some kind of vague or informal or heuristic guidelines for how good code should look, how clean code should look, well, one of the things that you want to be trying to achieve is splitting the program into its smallest components and having each of those as a procedure, and they're going to combine up the abstraction chain in order to create the program that you're actually writing. And while you're doing that throughout, if you're running in any strongly typed language, you do actually have, I want to say, like partial guarantees about the correctness of your program. Now, so it's more like a spectrum, even when we're hacking regularly, of correctness and incorrectness. Obviously, not all software has type systems as powerful as Haskell, or even within Haskell, there's not always, it can give a lot of guarantees, but there's a level which you can't. But so at that point, you're looking, okay, well, how much of the program itself can I actually move to compile time? How much of it can I actually make static, like metaprogramming? And then at that point, is the program itself its own proof? No, it's hard to say that, but it is some kind of formal specification of itself.
Could you give an example of that?
Well, let's say that I have something that says x equals x plus 1, as we did before. So in C++, I can actually create a template so that templates are all statically engineered. So I can actually create a template that takes in some kind of integer and returns that integer plus 1. And actually, C++ has simplified a lot of the ideas, so you don't necessarily have to do templates. You know, const expr, all one word, the new keyword that they added in, I think, C++ 11. encodes the idea of something being evaluated at compile time.
Mm-hmm.
So at that point, I'm not just saying that the compiler is going to verify for me, not just that I'm taking an integer, but also that I'm adding 1 to that integer. And that's something that the compiler's actually verifying for me as it's going through its type checking process.
So is that a baking in of some of these ideas into the C++ language then? They've moved a little bit of verification into a language construct.
Well, I mean, I think it's in part you get some guarantees on type correctness from any strongly typed language, or any type language even. But then the degree to which that type system can be leveraged in order to write programs themselves is, I think, what separates things where you can express something like that.
So when you look at serious theorem proving programs, okay, so yeah, some of you have now written simple theorem provers. You've written your MIU system software and so on. One style of programming that is in quite common use is to use a very strongly typed language like ML or Haskell to actually represent a type of theorems. Okay, so a formula can be a type, and then some formulas are also theorems because they've been proved. So if you can shove that into the type system, it's a bit like distinguishing integers from even integers, right? Some formulas are also theorems. So there are ways of building theorem provers that basically just shove all the work into the type system. Because if your type system can prove that this string is a theorem, then you're done. That's what a theorem prover is, right? You give it a string and you say, is it a theorem or not? So yeah, you'll see what we're going to talk about the rest of today is the other approach. This is where you take a program written in the conventional C-like language, at least, and you add this extra stuff on top of it. As we've done in the recipe, we've inserted these extra lines with these funny brackets around them. And yeah, here verification is something that's getting done on top of the normal system. But yeah, maybe it's a current trend to see these ideas going inside the languages themselves. As is often the case, when something starts to work, especially C++ will come along and gobble it all up and try and bring the ideas inside the language itself. Shall we take 10 minutes for a cup of tea? Yeah. Let's come back at.
Sounds good.
Let's come back at 15:35, and then we'll look at the. Go on. That's the preview. We'll look at the actual logic from 15:35. See you there.